Okay, good. Can you hear me at the back? Okay, good. So yeah, the title of my coffee talk today is Forming Black Holes from Stars. So if you go on Google and to news and search black hole, you'll see that in the past few months, there's been maybe 2 or 3 quite remarkable detections of black holes that we think come from stars. So the reason I want to give this coffee talk today is to hopefully equip everybody with the background knowledge, if you don't have it yet, to maybe engage in some of these discussions that are happening in this pretty exceptional time for black hole observation. So to understand them, we need to understand stellar structure first. So the basics are that any star, so some self-gravitating sphere, should have some pressure that is counteracting the inward gravity. So this is just called hydrostatic equilibrium. And for example, we can approximate that this pressure comes from the radiation from the nuclear fusion happening in the star. So that pressure is balancing the overlying mass, so that a star will kind of arrange itself to, for example, have some kind of density profile. So if we think of stars while they're burning hydrogen, so during the main sequence phase, burning hydrogen to helium, this is typically how a star will arrange itself in terms of the density. So you have this higher central density, and then it kind of peters out until what you define as the star's radius. And then if we consider, a star of any given mass, it seems like empirically and observationally that the radius of a star during the main sequence probably scales like m to the 4/5, so almost some linear scaling. So maybe the radius and the mass, for any mass, just looks, almost linear. So now it's useful to think of things in terms of a mean density. So given a star of some mass that arranges itself with this radius, what is the total mass divided by the volume? So for the case of these main sequence hydrogen burning stars, if we know some mass radius relation, we can say that the mean density rho bar, when you go through this using that, should scale inversely with the mass to this fraction, or equivalently the radius to that negative fraction. So the point here is that if you consider going to larger and larger masses, the average density of this star should get smaller. But what really happens kind of in the details is that, okay, on average, the density is lower, but as you get to higher and higher masses, you generally get more central condensation for the density. So in other words, you have higher rho C, or you can maybe think about it as some dimensionless central density divided by the mean density. So this just gets bigger and bigger for massive stars. So as you increase the mass. Okay, so now we can start thinking about stars that go on to form black holes. So I said a little bit about the central density getting bigger and bigger with higher mass. So this main sequence, hydrogen to helium, requires a temperature of on the order of 10 to the 7 Kelvin. But if you want to consider, okay, after hydrogen burning, when you have all this helium ash, how can I ignite the helium? You just need higher temperatures for those nuclear reactions. So these are now 10 to the 8. And then if you consider all of the successively heavier, ashes that get burned, silicon burning actually requires on the order of 10 to the 9 Kelvin. So burning heavier stuff, you need higher temperatures. You can really only achieve that for the sufficiently high central densities. And I just want to flag here that the key ingredient for forming a black hole is that these temperatures are high enough to reach silicon burning, or in other words, the masses are high enough to get there. So in the end, maybe simplification, but let's just say that the main sequence mass required to get to silicon burning is on the order of 10 to 100 solar masses, which is, at least in our galaxy, probably less than 1% of stars. Okay, so at this point, I will introduce the ion core. So I kind of talked about all these successive burning phases. So once you get to silicon burning, so the silicon burns and the main product is iron. So that is just the ash that's kind of left in the core that burns, and then it burns in kind of this silicon shell. So if you try and think about the densities in this iron ash core, it's like on the order of 1 billion grams per centimeter cubed, which is pretty out of this world. And it's so dense that actually the iron there is electron degenerate. So this is completely different to trying to understand, some material which has a pressure from, for example, a gas pressure or radiation. Instead, it's governed by this quantum Pauli exclusion principle, where the important thing to note is that in the case of an ideal gas, you have some temperature dependence on the pressure of the gas, and that may be familiar in our everyday experience. But in the case of degenerate material, we just have that the pressure actually doesn't care about the temperature. It only depends on the density. And that's because it is this quantum kind of law related to occupied energy levels and things like that. It actually doesn't care about the temperature. But you need to be sufficiently cold to be governed by that. So to give you a feel for the scale, this iron core that's so dense is maybe around 1,000 kilometers. And then some of the later ashes might go out to around 10,000 kilometers. But then the whole star itself is really, really big. So maybe at least on the order of the sun's radius, maybe. So if we do consider this simple degeneracy pressure, we can do the same thing. So you can do like dimensional analysis just with that, and get that the radius scales inversely to the mass to the power of a third. So that might look something like that. So you have the radius getting smaller as you increase the mass of this degenerate core. Now, if we think about this average density again, you get that it scales with the mass squared. So actually, unlike a radiation-supported star or gas, you have that the average density is still getting larger as you increase the mass. Or in other words, yeah, more massive is a lot smaller and a lot denser. So now we'll talk about when the iron core collapses. So yeah, I introduced this core here and said that the silicon overlying it is burning, and that's kind of the ash. Now, the reason that silicon was important, just to review this, is because if you think of, all of the chemical species or atomic numbers, remember that iron is kind of at this peak in terms of the binding energy per nucleon. So I guess in terms of having this hydrostatic sphere, beyond silicon, or sorry, beyond iron, nothing will actually kind of fuse naturally in this kind of equilibrium configuration of the sphere. So the point is that core will not ignite. Silicon above it will just keep burning and leave the iron ash underneath. And it can do that in principle until that degenerate core reaches the Chandrasekhar amount. And it's at this point, so there's some derivation of this, but at this point where you actually can't get the material more densely packed and still, be abiding by the rules from Pauli exclusion. So at this stage, you have many of the electrons are moving close to the speed of light. But yeah, the point is when you get to Chandrasekhar mass, some equilibrium no longer holds. That state kind of can't exist. So what happens is the iron core is no longer stable and collapses. And this happens over the order of 0.1 second, and then the material falls on the order of 0.1 of the speed of light. So you can imagine while this is happening, so we have this extreme electron degenerate iron core. It can't be supported by electron degeneracy pressure anymore, so it's collapsing. So, it's still kind of atomic stuff, but then it collapses. What you get is these kind of beta processes where you have the atomic stuff turning into neutrons and neutrinos, and there's many other combinations of that. But the point is you get this neutronization where you get atomic stuff getting down to nuclear densities because of these kind of captures that often emit neutrinos. So it's collapsed to about 10 kilometers in extent. So it was 1,000, around 1,000, now it's 10 kilometers. And now it's supported by neutron degeneracy pressure, which is larger than you can get from electrons. So, okay, we had this super compact 10-kilometer star form in the core. You can imagine, everything else around it is also falling into the center as well, behind it. So, okay, you have a lot of stuff coming in. Maybe some of it is accreting onto this new neutron star, but this is happening at such a rate that you expect most of the material should kind of bounce back in a supersonic shock going back out. And to give you a feel for the new kind of density here, so we've gone from 1 billion grams per centimeter cubed to 10 to the 14th. So this is really nuclear density. And because it's neutron degeneracy supported now, there's a new maximum mass that is maybe more uncertain than the Chandrasekhar one for how much mass can this have before it becomes unstable like the iron core. So in terms of forming the black hole, well, we have a neutron star at the moment. So one thing we need to consider is that during both the formation of that neutron star and then subsequent possible accretion of some of this material, these will undergo these beta processes that emit a huge amount of neutrinos. And what people think might happen is that so the neutrinos are emitted, and they can kind of accelerate the shock because the energies are comparable, maybe to the energy associated with the shock, just from neutrinos. So yeah, there's basically two options, kind of related to what exactly this shock can do. So the first is basically if there are some processes that can accelerate this shock and prevent it from stopping, because it's blasting out into this iron-rich material, it actually can ignite and cause these kind of fission reactions that weren't really allowed in the hydrostatic phase. So, the shock loses energy doing that, and it can in principle stop. But then there's these neutrinos that can, provide the energy to accelerate it. So there's some kind of balance that's a bit unclear, but perhaps it's possible that this shock reaches the surface and has a velocity larger than the escape velocity and can eject a lot of material at the surface, which is kind of a funny concept if we consider that things are kind of collapsing. But anyway, the stuff out to there might be on the order of 10 solar mass. So what happens is you get some fraction, maybe on the order of or order of 10% of the total mass getting blasted off because of that shock wave from bouncing. So in this case, you get stuff ejected off, so you should see a supernova. And all of these elements that got synthesized with the fission reactions as the shock blasted through, you should see them in a supernova-like curve. So I think that's nice, but then sometimes in the case that this shock, maybe it does reach the surface, but it can't kind of unbind the outer region. You just get the eventual complete collapse of like all of the material into a black hole, which is maybe kind of sad because all of these interesting neutrino hydrodynamics and nucleosynthesis are happening from this shock wave. But in the case that you get complete collapse, you just will never see anything. So in the first case, where you get stuff blasting off, maybe the maximum black hole mass, just because of all the ejected material, is only up to like 10 solar masses. But then when you get this complete collapse, you can probably get much higher masses. So the final thing I just want to say about black holes, so, okay, whatever the mechanism is, we can say it maybe spans an order of magnitude in the possible masses. So I kind of want to come back to this concept of mean density, because we know that the event horizon, or let's think about it like a star, like the physical radius is like this, so it goes like the map. So if you think of the mean density gets lower with larger radius or mass. And then if we consider like the counterintuitive degeneracy pressure and mass radius relation, and then the one for stars here, you'll see that if you think about this kind of average density for a black hole, it ends up being more similar to like the main sequence stars, which I don't know, I think is kind of strange. I think that would lead to something more exotic, but maybe you kind of, if you think of them kind of like stars, maybe it's fine in that, the main sequence stars are more centrally condensed. And I know a black hole is like a singularity, but maybe yeah, maybe it's actually consistent to think, okay, it has a smaller mean density with increasing mass, but actually it's fine because it's just more severely. But anyway, yeah, I hope that yeah, this is enough to kind of appreciate some of the weird black holes people are finding. And sorry to go a bit over time.
Thank you very much. Thanks. I'm interested in the structural style of the problem. Yeah. So, so the inner side is iron.
Yeah.
The next is the. So my question is that yes, it is it is a way to understand the structure. I mean, is there any observable evidence to support this kind of structure? So I mean, of course, we may assume that is a structure. But still, we want to say whether this is indeed the case.
Well, yeah, probably. So I think with supernova light curves, some aspect of that is looking at the spectra. So what kinds of elements could you see in like the light from the supernova?
But still, they can infer from the spectrum. They can infer the location of the element. I mean,
No, but I think at least according to stellar modeling, which simulates the entire lifetime of the star, that should make predictions about roughly, because the key thing is, I guess, exactly when enough of this is burned to trigger the 100 AR mass limit. So I think people do compare. So yeah, sorry. I think the key thing is how much ash, like for different elements, how much ash is there from a given stellar model. But yeah, in terms of an actual way to like check this specific structure, I don't know, but I think it's well like supported by theory and hydrodynamics. That the heavy stuff kind of thing.
At least from spectrum, we can, although we cannot show the structure of this stuff, but we know the element of it.
Yeah, exactly. So sometimes people see supernovas that have like no helium, for example. So then they say, oh, it must have lost its helium layer or something. And then, yeah, there's also elements produced like radioactive nickel that maybe if you look at the amount of that and compare it to what you think of the structure before it does this kind of explosion, maybe you can do some comparison too and say like, do I have enough? Yeah, do I still have enough? Or did I make enough iron to get that much nickel or something? But yeah.
You gave two numbers. They may result in the research area of forming black holes from stars.
I think so, yeah.
The argument is very solid, or there is a lot of subtlety in deriving these numbers.
Yeah, so there's some subtlety in that. I think these estimates are from assuming that the initial star had no metal at all. So they were like the first, made of the first material in the universe. But then I think as soon as you add heavier metal to even just stellar evolution, for example, you can get some of these outer layers being blown up in some winds related to radiation. So yeah, basically there's kind of another dimension to these numbers related to how much elements heavier than helium were in the star when it was born, kind of thing. So yeah, seeing a black hole, and for example, if it was 20 solar mass, I can't say, oh, it definitely came from some explosions, because if you look in the other, metallicity kind of plane, that could explain it for a direct collapse simulation and so on. So yeah.
These numbers can be tested experiment or being tested observationally.
Yeah, I think so. So I picked this number purely from numerical simulation, and I think also there's I think there's no black hole between what people think this limit is and maybe around 4 or 5. But yeah, I think recently there was a detected black hole in that lower bound, I think. So maybe maybe the upper limit is subtle, but this lower limit I think is easily testable. And yeah, maybe people think there is no lower limit now. At least it should still be bigger than this, but yeah, there might be no lower limit.
Very nice. Also, my question is, what's the lower bound of the initial mass to form a black hole? So how much? Yes.
Yeah. Oh, sorry. I think it needs to be and let's say 10 solar mass on the main sequence.
Oh,
yeah. Well, it's small, but still very rare. Yeah.
So you start in a mostly spherically symmetric case. How spherically symmetric does this process remain as you go to smaller and smaller?
So I think basically until it burns silicon, the time scale for the nuclear burning that is providing the pressure is really, really slow. In terms of setting the structure that people often kind of neglected in hydrodynamic simulations and stuff. But I think when you get to silicon burning, like the burning time scale is like 1 day, and I think the dynamical time scale of the star is like 1 hour. So I think I would say that it becomes important then, just based on time scale stuff. But then the explosion is also very asymmetric. And for example, like if you get, what people see in simulations is, so okay, you have this shock wave, and then you have this neutrino heating, and actually this region is turbulently convective, and you can get like kind of large scale asymmetries, kind of pushed even like larger by the neutrino heating and stuff. So I think, yeah, that's important, and it should lead to like observable things such as the spin of the neutron star, or it being like kicked because of, if there's some asymmetry in the accretion, and then, things kind of get blasted off, you can get just like linear momentum kicks of the neutron star. So people actually can observe that as well. They're kind of moving really fast. Yeah. So I personally think it's important then, mostly about the compact room.
Yeah, great.
So, maybe to Idan's question, but so if some observation finds like black hole, I know black hole of the mass
So maybe if you found a lower one, if you found a black hole that was like 2 solar masses, then it may be challenging this limit, because then it's like, how did we make this collapse completely if it didn't exceed that limit? And then in terms of the higher mass end, I think, yeah, if you don't know anything about the metal content, I think you can go up to, I think it's like 140. 140 solar mass, like initially, I think, because when you have these really massive stars, they actually destroy themselves through like positron pair annihilation. So that's a different kind of supernova. So that's a pair instability supernova. And I think there's one star that's possibly evidence for that happening. So it was kind of like, I mean, it makes sense theoretically, but basically I think they found just a really old normal star in our galaxy, but then took the chemical spectra and then said, oh, like a pair instability has to explode on it to get its weird like atmosphere or something. So yeah.
Is it that kind of star has to have very high spectroscopy? Sure.
Oh, like I think no, it can have low metallurgy.
So this is the only way to form black hole, or there's other way?
Yeah, I think there's people think like primordial black holes from the early universe could be a candidate to make like, I don't know, 1 solar mass or less black holes. And I think there's also in the early universe, like when galaxies or stars were forming, I think there's a channel which is like the collapse of a gas to a black hole. But I'm not so familiar with that. But
Okay, so then let's thank Lucy again.